So in this lecture, we're going to look at some examples of these binary representations and get a little practice taking these and converting them back into decimal numbers. And this is all going to be by way of getting some practice in for the next lecture where we start talking about the specific limitations of this method. All right, so I've got a number here for us to look at. It starts with a leading 0. Then it's 1 followed by 11 zeros, then 1 followed by 51 zeros. So what is the decimal equivalent of this number? All right, well, the S value is 0. That's our power of -1 here, so we can see our number is going to be positive. And we have this 11-digit binary number here. Now remember, the first digit is 2 to the 0, which means this last digit is 2 to the 10th. Right, so the C is 1 times 2 to the 10th, which is 1024. So I'm going to put that in here for my exponent. It becomes 2 to the 1024 minus 1023. Okay, so that, obviously that's going to be 1, right? So our exponent is going to end up just being 2. Our exponent part is going to end up being 2. All right, so what's the significant here? Well, remember that this is a binary fraction. Right, so this is going to be 1 times 1/2 to the first plus, and it's zeros from there on down. So this is just 1/2. Or we're doing decimals here, right? So we can just go ahead and make that 0.5. So this will be 1 plus 0.5. All right, so now it's just an arithmetic problem. -1 to the 0 power is 1. This is 2 to the first, which is 2. This is 1.5. So this whole expression here is equivalent to the decimal number 3. So I've got another example here, and you're welcome to pause the lecture if you like. See if you can't work through this on your own, right? Then come back and check your answer. So we're starting off at the same place with S. That's 0. So we're doing a positive number here. My value of C, remember this is 2 to the 0, so this is going to be 2 to the 9th. 2 to the 9th is 512. So C will be 512. 2 times 512 minus 1023. What do we have here? This is 1/2 plus, that's 0 times 1/2 squared, plus 1 times 1/2 to the third, plus 0 1/2 to the fourth, plus 1 1/2 to the fifth, right? First, second, third, fourth, fifth, yes. And everything else from there on down is 0. So this is going to be my value of F. If you go to your calculator, work this out, this comes out to 0.65625, which means when I add the 1, this is 1.65625. And what's my exponent here? This ends up negative 511. So -1 to the 0, that's 1. So this is 2 to the negative 511th power times 1.65625. Okay, 2 to the negative 511. That is a really, really small number. Excuse me. There are websites that you go to, and I'm actually going to give you a link to one in the last slide, that will take these binary representations and convert them into decimal digits with all the possible exponents. And I actually went ahead and did that here. This is the decimal value to all of the available precision of this binary representation. So before we go on, I've got 4 special numbers that you should be aware of. These are numbers that, while technically you could plug these numbers into the formula and get a result, uh, that's not what they're going to be equal to. These numbers have special definitions to cover some kind of unusual values that we want to have numbers for. Right? So if you look at our formula, right, -1 to the S times 2 to some power times 1 plus F. Right, this number here, -1 to the S power, this is not equal to 0. This number here, the exponent, that's Well, it's an exponent, right? It's an exponential function. This number is also not equal to 0. And while it's possible for f to be equal to 0, when I add 1 to it, it's never going to be equal to 0 either. So we have a little bit of a problem here. There is no way to represent 0 using our binary representation system. And that is a problem, because obviously we need to have a way to represent 0. So the way we do that is we just kind of arbitrarily define any number whose exponent part is 0 and whose significand is 0 to be 0. Right? And now down here, what if the significand is not 0? Well, if the exponent part is 0 and the significand isn't, then this is used to define what are called subnormal numbers. And we're really not going to talk about those. It's kind of beyond the scope of what we're doing in a numerical analysis class. But that's a way that the computers can kind of sneak in numbers that are below the minimum number that would otherwise be possible. We're going to talk about what that minimum number is in the next lecture. So the next one here, if the exponent is set to its maximum value, right, that's going to be 2 to the 11th minus 1 in decimal, and the significand is 0, this is defined to be infinity. Right? And finally, if the exponent is set to its maximum and the significand is any other number, this is defined to be what's called not a number. Okay, kind of weird, but some programming languages, they use that for various things. Well, we'll see a little bit of that as we go along here. So converting back and forth between our binary encoding and decimal digits isn't something that's really going to be a big part of our study of numerical analysis. What we are interested in is how the limitations of this necessity impacts the calculations that we're going to be doing as part of implementing the kinds of algorithms that are a part of numerical analysis. And understanding this encoding scheme is going to be a big part of that. So if you ever find that you do need to either encode or decode a number, there are plenty of websites like the one I've listed here that will do that for you. Or you can even write your own little utility program to do it. If you do choose to go that route, there are a couple of pitfalls you should be aware of. First, if you're using a website, be sure you're using one that's encoding a 64-bit double value. There are also websites that will do the older 32-bit schemes, and double is the general term used in software development to refer to a decimal number with a maximum possible value. And that's in contrast to integers and what are called single floating point numbers. Now, if you're trying to write your own application to do this, you should also be sure to test it with numbers that are either very small or very large. Right? I have a little Excel spreadsheet that does this conversion, and it has trouble with values at the high and low ends of the scale, since Excel's level of precision is actually lower than the operating system standard. Okay, so that brings us to our next topic. In the next lecture, we're going to look at some of the limitations of this encoding method, including things like finding its maximum minimum values and values where rounding error starts to become a concern.